Good day, students, and welcome to the video from Digital Systems 1, Functions of Combinational Logic, or the first one for study unit 6. Okay, so in this study unit, we were looking at combinational logic circuits and or invert ICs, adders, comparators, decoders, encoders, code converters, multiplexers, demultiplexers, and parity generators or checkers. All that logic that we went through, and we're now going to implement it with logic circuits. But first we start with adders, not the snakes, just mathematical adders, so adding one binary number to another. So we will be working with two basic types, half adders and full adders. Half and full adders do the same job of adding binary numbers. Difference is that a full adder has an input carry. I'll just become more clear later on. So this is the how we write a full adder, how we draw the diagram of a full adder. So A and B are the input bits. You have the sum and the carry. Notice you don't have an input bit for the carry that goes into it. Here's a truth table for the half adder. A and B inputs, and the carry, and then the sum. So 0 and 0, adding 0 and 0, we don't have any carry, and it's 0. 0 and 1, no carry, 1, and 1 and 0, no carry, 1, and 1 and 1, you have a carry, and sum 0. So from that truth table, we can generate this logic circuit. This is for the carry out, and we have an exclusive OR gate for the sum. So this is a AND gate, exclusive OR gate, and that makes our half adder circuit. Now the full adder is slightly bit more complex. Here we have an input carry and input bits through the sum and output carry on the outside. So the full adder truth table is a bit more complex, and here we have the carry bit inside, and A and B, that's the numbers added, and carry in. So A and B with no carry is 0, A and B with a carry of 1 is 1, same here, 1. B, A, B, and C with a carry of 1 is 1 and 0, same 0. A carry of 1 is 1, 0. A and B is carry of 1. And you have A, B, and C. You have a carry of 1. And the sum is 1. So this design is slightly more complex. So if we don't care about this for the sum of 3 bits. So we use that, sum of 3 bits. And that just gives you the sum of 3 bits. But it doesn't give you the carry. So here, and this logic bit circuit is for the carry. Okay, so that 2 exclusive OR gates just for the sum, and the 2 AND gates, and the OR gate is for the carry out. So here we can have 2 half adders, which makes up a full adder. So 2 adders here. We don't have a carry bit, but the carry bit here is for the second adder is B, and then the sum would be there, and then this would represent the carry bit. So now the question comes: design a full adder sum of products. So this is the truth table for a full adder. P and Q are the inputs, the carry in, carry out, and the sum. Just as the other one is. So we fill in the truth table exactly the same as the previous full adder truth table. And as we did before, and for the sum, we look at where there's ones, and then we write down the equations where there's ones. And the same for the carry out. Wherever there's a 1, we write the equations. So this is basically the equations that define our full adder. Now, we're trying to minimize it. For the sum, the carries are like this, which means we can't group more than one at a time, so it cannot be minimized. So the sum stays the same. Now, in order for us to add up bigger binary numbers, we can use a number of adders arranged in parallel. We get dedicated ICs that are used for adding, and here we will look specifically at 74LS283. It's an IC that can add up a 4-bit binary number, and it looks like this. So here we see that's the VCC, that's the power, and that's the ground. We have the sum 1, 2, 3, and 4. That is on this side. So these numbers in brackets are the actual pins on the IC. So here is the number for A and B, the ones we're going to be counting together. So 5 is there, A1, A2 is 3. So here, so A1, A2, A4 and A3, that's the first, that's how we wire up for the first number to be added. And then the B, 6, 6 and B3, okay, so there is the second number to be added. And then 7 is the carry out. Here we have the sum, the result of the equation, which is the first bit is at number 4, number 1, number 13, and number 10. And then the carry out is C4. So here you would, this is how you would wire up the this IC to do 4-bit adding. So if we want to add 2 4-bit numbers to add up an 8-bit number, this is how we would wire the 2 ICs. Very important. The first carry we wire to ground, which means that it's a 0 because there's no previous carry. And then we wire them up in parallel like this, where you would have the upper nibble of the one binary number, the lower nibble of one binary number, upper nibble of the other binary number, and the lower nibble of the other binary number. And then this would be the carry out, and these are the results. This would be the result of the addition. Bearing in mind, from the one IC to the other, we have this carry out, which becomes the other IC's carry in. Here we use exactly what we said, the 2 ICs to add an 8-bit number. So here is we start with the lower nibble of the 2 numbers and wire them up like this, and then they would become the lower nibble of the answer. So here we'd see you have adding A1 and B1 is 1 and 0 is a 1. A2 and B2, 0 and 1 is a 1. B3, A3, 0 and 1 is a 1. And B4 and A4, 1 and 1 is a 0 with a carry of 1. Okay, to the next IC. So here we would have the lower nibble of the answer, and here we have the upper nibble of the answer. And these are the upper nibble of the 2 numbers being added. And then here you have a carry of 1. So that is quickly the video on adders. It's pretty simple if you go through a couple of examples, and it's basically just binary numbers being added together, and the ways we do it using different logic circuits. All right, good luck.